40 billion. That's how many Earth-sized planets might exist in our galaxy alone, nestled in zones where life could thrive. 40 billion chances for chemistry to ignite, for civilizations to rise. Yet, after decades of relentless searching, listening with our most advanced instruments, we found exactly zero. No confirmed signals. No technology. Just a deafening cosmic quiet. But what if this silence isn't emptiness? What if it's the most profound message the universe could send? To truly grasp its meaning, we must first understand the universe's ultimate speed limit. The speed of light. Nothing we've ever measured, nothing physics permits, moves faster. In just 1 second, light travels 186,000 miles. That's fast enough to circle the entire Earth 7.5 times before you finish blinking. It crosses the distance from Earth to the Moon in just over a second. It reaches the Sun in 8 minutes. At these scales, light feels instantaneous. A flicker. A thing that happens and is done before you even register it. But space is not Earth. Space is not even our solar system. Space is something so much larger than either of those things, that the speed of light, the ultimate speed limit of the physical universe, begins to feel agonizingly slow. To understand why, you have to sit with what light actually does during a full year of uninterrupted travel. Multiply 186,000 miles per second by 60 seconds in a minute. Then by 60 minutes in an hour. Then by 24 hours in a day, then by 365 days in a year. Every second, of every minute, of every hour, of every day, light moves at its maximum possible speed, never slowing, never stopping. The result of that multiplication is 1 light year. Roughly 5.88 trillion miles. 12 digits, sitting in a row on the page. And the human mind slides right off them, because we have no lived experience that makes a number like that feel real. So, let us try to make it that way. If you wanted to drive 1 light year at highway speed, maintaining 60 miles per hour without ever stopping for fuel, or sleep, or food, the journey would take approximately 11 million years. Not 11 million days. Not 11 million months. 11 million years. Anatomically, modern humans have existed for roughly 300,000 years. You would need to stack our entire species' history end to end more than 36 times just to drive a single light year at highway speed. And a light year is just the unit. It's the ruler. It's the smallest convenient measure we have for describing the distances between stars. The nearest star to our Sun is Proxima Centauri. It sits 4.24 light-years away. That means light leaving Proxima Centauri right now will take 4 years and 3 months to reach Earth. The fastest spacecraft humanity has ever launched, Voyager 1, has been traveling continuously since 1977. Nearly 5 decades of uninterrupted flight through the outer solar system and beyond. As of today, Voyager 1 is approximately 15 billion miles from Earth. The most distant human-made object in existence. A number that sounds enormous, until you compare it to what it would take to reach even our nearest neighbor. 1 light-year is 5.88 trillion miles. Voyager 1, after half a century of flight, has covered roughly 0.25% of a single light-year. At its current speed, that spacecraft would need approximately 73,000 years to reach Proxima Centauri. Not to cross the galaxy. Not to reach another civilization. Just to reach the single closest star to our Sun. 1 star. 4.24 light-years. 73,000 years at the fastest speed we have ever achieved. That comparison isn't meant to make us feel small, though it does. It's meant to establish something precise about the nature of the cosmos we live in. The distances between stars are not merely large in the way that oceans are large. They are large in a categorically different way. A way that places them entirely outside the reach of anything we have ever built, or are likely to build in any near future. The light year is not a poetic exaggeration. It is a practical necessity. Without it, the numbers required to describe even nearby stellar distances would be so unwieldy that astronomy would collapse under its own arithmetic. And yet, the light year is only the beginning. Once you have the unit, once you have internalized what 5.88 trillion miles means in terms of time and speed and the limits of human engineering, the universe immediately asks you to scale up. Because Proxima Centauri at 4.24 light-years is not typical. It is our closest neighbor, and it is already at a distance that makes every form of travel we have ever invented look like standing still. Most stars in the Milky Way are tens, hundreds, or thousands of light-years away. The galaxy itself stretches 100,000 light-years from one edge to the other. And beyond the galaxy, the distances involved stop feeling like distances at all, and begin to feel like something closer to geological time. But before we get there, there's one more thing the light year does to your understanding of the universe that goes beyond simple distance. Something that changes not just the scale of space, but the nature of what we are actually seeing when we look at it. Light travels at a fixed speed. That means every object you observe in the night sky, you are not seeing as it is. You're seeing it as it was. The light entering your eye from Proxima Centauri left that star more than 4 years ago. You're receiving a message sent in the past, arriving in the present, from a source that may have changed in ways you cannot yet know. This is not a technicality. It is not a minor footnote. It is one of the most fundamental and disorienting truths in all of science. Point a telescope at a star 1,000 light-years away and the light you collect departed during the Middle Ages. Before the printing press existed. Before the Renaissance reshaped European thought. Before any European sailor had crossed the Atlantic. The star you are studying may have changed dramatically in the 1,000 years since that light began its journey. It may have dimmed. It may have brightened. Under extreme circumstances, it may no longer exist at all. You would not know yet. The news has not arrived. Aim at the Andromeda Galaxy, our nearest large galactic neighbor, at 2.5 million light-years, and you are receiving light that began its journey when our ancestors were still learning to shape stone tools on the African savanna. Modern humans did not yet exist. The species that would eventually build radio telescopes and ask questions about the cosmos were still hundreds of thousands of years from drawing its first breath. And yet the light from Andromeda was already in transit, already crossing the void, already heading toward a planet that had not yet produced anything capable of receiving it. This is what the light year does to time. It does not just measure space. It folds the past into every observation we make. Every photograph ever taken through a telescope is a historical document. Every spectrum analyzed, every wavelength recorded, every signal processed, is archaeology. We're not seeing the universe as it is. We're assembling a portrait of the universe from light that departed at thousands of different moments across billions of years of history. All arriving at our instruments simultaneously. Like letters posted centuries apart, landing in the same morning's mail. The light year is the unit that makes this possible to describe. And once you understand it, the night sky is never quite the same again. It stops being a ceiling and becomes a timeline. Every point of light, a message from a different depth of the past, arriving now, telling us what once was. The cosmos, therefore, is not a present reality we observe. It is an immense, silent archive. And every single flicker you witness in the night sky is nothing more than a ghost. A whisper from a past so distant, it might as well be a dream. A dream of what was, across billions of years. A terrifying truth, when you look up, you are staring into the face of one, single, unimaginably ancient silence. Our home galaxy, the Milky Way. A shimmering spiral of gas, dust, and somewhere between 200 and 400 billion stars. Bound by gravity, forming a disk roughly 100,000 light-years across. Imagine yourself floating above it. Our sun. Just a minor speck, tucked away in an unremarkable neighborhood, 26,000 light-years from its bright central bulge. To cross this magnificent structure, from one edge to the other, even at the speed of light, would take a staggering 100,000 years. Let that number sink in. The entire recorded history of human civilization, from the first cities to the satellites orbiting Earth, spans roughly 10,000 years. Crossing our own galaxy at the maximum speed the universe permits would take 10 times that long. If you send a message from one side of the Milky Way and waited for a reply, the round trip would devour 200,000 years. Our entire species' history would not be enough to hold a single conversation across the galaxy we inhabit. But the Milky Way is not large by cosmic standards. The Andromeda Galaxy, our nearest large neighbor, is roughly the same size, but contains perhaps 1 trillion stars. It sits 2.5 million light-years away. Light leaving Andromeda right now will not reach Earth for 2.5 million years. When that light departed, the genus Homo did not yet exist on Earth. Our ancestors were something earlier. Something that had not yet developed language, or tools, or fire. The faint smudge you can see on a clear night is showing us a world from before our species existed. A ghost of a galaxy from a time before us. Between the Milky Way and Andromeda lies the local group. More than 50 galaxies spread across roughly 10 million light-years of space. The Magellanic Clouds, visible from the southern hemisphere, are among the closest companions. The Large Magellanic Cloud sits about 160,000 light-years away. Astronomers studying the supernova that exploded in the Large Magellanic Cloud in 1987, the brightest supernova visible from Earth in nearly 400 years, were watching an event that occurred 160,000 years ago. The star died before modern humans walked the Earth. Its light only arrived in 1987. Beyond the local group, the scale shifts again. Galaxy clusters, collections of hundreds or thousands of galaxies, are separated by tens of millions of light-years. The Virgo cluster, nearest large cluster to our local group, sits 65 million light-years away. Light leaving the Virgo cluster today will not reach Earth until long after every species currently alive on this planet has either evolved into something unrecognizable or disappeared entirely. When that light began its journey, the dinosaurs had been extinct for less than 1 million years. Mammals were only beginning to diversify. The light crossing your eye from those distant galaxies is older than every land mammal alive today. You are seeing light from a time before your ancestors' ancestors had truly begun to walk the Earth. Superclusters are the next level up. The Laniakea supercluster, containing our local group and roughly 100,000 other galaxies, stretches 520 million light-years across. It was only fully mapped in 2014, revealing our slow drift, along with hundreds of thousands of other galaxies, toward a gravitational center they named the Great Attractor. A point in space roughly 250 million light-years away. We are not stationary. We are moving, invisible to us on any human time scale. But before we lose ourselves in unfathomable depths, let's bring it closer. The light-years implications permeate even our immediate cosmic neighborhood. Every time you look at something in the universe, you are not seeing it as it is. You are seeing it as it was. And the further away it is, the further back in time you're looking. This is not a metaphor. It is a precise physical fact, with measurable consequences for every observation. Light leaving the sun takes 8 minutes to reach Earth. The sun you see right now is the sun as it existed 8 minutes ago. If something catastrophic happened at this exact moment, you would not know for 8 minutes. For 8 minutes, you would be living in a present built on a past that no longer existed. That 8-minute delay is trivial. But extended outward. The moon reflects sunlight that is about 1.3 seconds old. Mars, at its closest, is 3 to 22 light-minutes away. Jupiter, 33 to 53 light-minutes. Saturn, the furthest visible to the naked eye, 70 to 100 light-minutes. Every photograph of Saturn by the Cassini spacecraft showed scientists a Saturn that existed at least an hour before the image was received. Our solar system alone introduces minutes to hours of delay. Move beyond, and delays become historical. Sirius, the brightest star, is 8.6 light-years away. Its light tonight left in 2016. Betelgeuse, the red supergiant in Orion, is approximately 700 light-years away. Its light departed during the early 14th century, around the time the Black Death swept Europe. Astronomers watching Betelgeuse for signs of instability are watching a star as it existed 7 centuries ago. Betelgeuse may have already exploded. The light from that explosion, if it happened, is somewhere between here and there, crossing the void. It has not yet arrived, carrying news that will not reach us for decades or centuries. Imagine the silence, the slow, agonizing crawl of light, carrying the news of a star's death, an event that has already happened 700 years ago, but remains utterly unknown to us. That's the chilling reality the light year paints, a universe where news travels slower than time itself, and the most dramatic events are always just, out of reach. In February of 1987, astronomers detected a supernova in the Large Magellanic Cloud. This small companion galaxy to the Milky Way sits 160,000 light-years away. It was the closest supernova observed since the invention of the telescope. Bright enough to see with the naked eye from the southern hemisphere. Astronomers scrambled to study it. They analyzed its light curve, its spectral signature, the neutrinos that arrived at underground detectors hours before the visible light. Neutrinos, you see, travel through stellar material faster than light can escape an explosion. They identified the exploded star by looking at archival photographs. It had been a blue supergiant, catalogued decades earlier, giving no obvious indication that its core was about to collapse. The explosion itself occurred 160,000 years before anyone on Earth saw it. The star died before modern humans existed. Its death cry crossed 160,000 light-years of space and arrived in 1987. And we just happened to be watching. The further you look, the deeper into the past you see. The more dramatic the consequences of that delay become. The Andromeda Galaxy, at 2.5 million light-years, is showing us a galaxy as it existed before our genus even evolved. The Virgo cluster, at 65 million light-years, shows us galaxies as they existed when the first large mammals diversified after the extinction of the dinosaurs. The most distant galaxies ever observed by the James Webb Space Telescope sit more than 13 billion light-years away. The light arriving from those galaxies left its source when the universe was only a few 100 million years old. These are not mature galaxies. They are infants, ragged and irregular. Burning through their first generation of stars, forging the heavy elements that would eventually seed later generations with the raw material for planets and chemistry and life. What the James Webb Space Telescope is doing, in a very precise sense, is looking at the universe's childhood. Its infrared instruments are tuned specifically to detect light that has been stretched by the expansion of space during its billions of years of travel. Shifted from its original wavelengths into the infrared range. The way a sound stretches and deepens as its source moves away from you. The further the galaxy, the more its light has been stretched. The redder it appears in the data. Cosmologists call this red shift. And it is one of the primary tools by which they measure not just distance, but the history of the universe itself. Every galaxy in the Webb Deep Field images is a data point in a timeline stretching back nearly to the beginning of everything. The telescope is not just a camera. It is a time machine, pointed in one direction, backward. There is something quietly unsettling about this when you follow it to its conclusion. The universe we observe is not the universe as it is. It is a composite of different pasts layered on top of one another. Each object in the sky broadcasting from a different moment in history. The star 4 light-years away is showing you 4 years ago. The galaxy 65 million light-years away is showing you 65 million years ago. The faint smear of light at the edge of the Webb Deep Field is showing you 13 billion years ago. All of these images arrive simultaneously. Stacked into a single moment of observation. Creating the illusion that we are seeing one universe, at one time. We are not. We are seeing thousands of different universes, at thousands of different times. All collapsed into a single photograph. This has a consequence that is easy to overlook, but impossible to escape once you see it. We cannot know the present state of the universe. Not even in principle. There is no observation we could make, no instrument we could build, no technology we could develop that would show us the universe as it currently exists across its full extent. The present state of a galaxy 100 million light-years away is inaccessible to us by the laws of physics themselves. By the time any information about its current condition could reach us, 100 million years will have passed. What we call the observable universe is more accurately described as the historical universe. A record of what existed at various points in the past, assembled into a map we study as though it were a snapshot of now. It is not a snapshot. It is an archive. And yet this limitation, this fundamental barrier between observation and present reality, is also one of the most powerful tools science has ever possessed. Because the fact that we can see the past means we can study the history of the universe directly. We don't need to infer what early galaxies looked like from theory alone. We can point a telescope at them and observe them in the state they actually occupied billions of years ago. The light year, by introducing delay into every observation, has given us something extraordinary. A record of cosmic history written in light. Preserved across unimaginable distances. Delivered to our instruments across billions of years of travel. Still carrying the information it encoded at the moment of its departure. The universe is its own archive. And the light year is the key that tells us how far back each entry was written. There's a number cosmologists use to describe the expansion of the universe. It is one of the most consequential measurements in the history of science. It's called the Hubble constant, named after Edwin Hubble. The astronomer who, in 1929, demonstrated that the universe is not static. Not fixed. Not the eternal, unchanging backdrop that scientists and philosophers had assumed for centuries. Hubble showed that distant galaxies are moving away from us. And that the further away they are, the faster they are receding. The universe is expanding. It has been expanding since the moment of the Big Bang. And that expansion changes everything about how we understand light years, distances, and the ultimate limits of what we can ever know. The discovery did not come easily or cleanly. Hubble spent years at the Mount Wilson Observatory in California, using the 100-inch Hooker telescope, the most powerful instrument of its era, to study faint smudges of light that astronomers of the time called spiral nebulae. The prevailing view was that these nebulae were clouds of gas within our own galaxy. Hubble proved they were not. By identifying a specific type of pulsating star, called a Cepheid variable, within the Andromeda Nebula. He used the known relationship between a Cepheid's pulsation rate and its true brightness to calculate its distance. He determined that Andromeda was far too distant to be part of the Milky Way. It was a separate galaxy. An island universe in its own right, sitting millions of light-years away. The Milky Way was not the universe. It was one galaxy among many. That single finding expanded the known scale of the cosmos overnight by a factor no previous scientific discovery had matched. But Hubble did not stop there. By studying the light from multiple galaxies and measuring the degree to which their light had been stretched toward the red end of the spectrum, a phenomenon called red shift, caused by the Doppler effect as sources move away from an observer, he found a pattern. Galaxies further away showed greater red shift. They were receding faster. The relationship between distance and recession speed was consistent enough to be expressed as a mathematical ratio, the Hubble constant. For every megaparsec of distance, roughly 3.26 million light-years, galaxies are receding at a speed that current measurements place at between 67 and 73 kilometers per second. The precise value is still debated. A tension in modern cosmology that has not been fully resolved. But the principle is not in doubt, space itself is stretching. Galaxies are not moving through space away from us. The space between us and them is growing. This distinction matters enormously for understanding light-years at cosmological scales. If galaxies were simply moving through static space, the light-year would be a straightforward ruler. A galaxy 1 billion light-years away would have its light take 1 billion years to reach us. End of calculation. But because space is expanding during the journey, light traveling across vast distances is doing so through a medium that is continuously stretching beneath it. A photon that left a distant galaxy 13 billion years ago was not, at the moment of its departure, 13 billion light-years away from Earth. It was much closer. But the space it had to cross kept expanding as it traveled. Stretching the journey. Shifting its wavelength. Increasing the effective distance it needed to cover. By the time it arrives, the source that emitted it has been carried much further away by the expansion of space itself. This is why the observable universe has a radius of 46 billion light-years, despite being only 13.8 billion years old. The two numbers are not in conflict. They are a direct consequence of expansion. The most distant light we can detect left its source roughly 13.8 billion years ago, when the universe first became transparent to radiation. But the region of space that emitted that light has since been carried 46 billion light-years away from us by the ongoing expansion. We are seeing that region as it was 13.8 billion years ago, from a position it no longer occupies, across a distance that did not exist when the light was emitted. The light-year measures the journey the light actually took. The current distance to the source is a separate calculation, one that requires knowing the full history of cosmic expansion over 13.8 billion years. Beyond the observable universe, the expansion introduces something even more absolute than distance. There is a boundary. Not a physical wall, but a cosmological horizon beyond which space is receding from us faster than light can travel. Regions of the universe beyond this horizon are not merely far away. They are causally disconnected from us. No signal, no light, no information of any kind can ever reach us from those regions. Not because anything is moving faster than light through space, but because the space between us and them is growing faster than light can cross it. Those regions exist. The laws of physics do not prevent them from containing galaxies, and stars, and chemistry, and perhaps life. But they are permanently beyond our reach. Not just practically, but in principle. The universe is larger than the observable universe by an amount we cannot measure, possibly infinitely larger. And we will never know what it contains. This ultimate horizon, the unseeable, unreachable edge of our existence, means that the vastness is not just a challenge to our technology. It is a fundamental, terrifying truth. A truth that whispers, there is an entire cosmos out there, forever locked in silence, permanently beyond our knowing. A silence so profound, it truly defines the limits of our universe. Expansion also means that the universe had a beginning. A moment before which the concept of distance, as we understand it, did not apply. Wind the expansion backward, and every galaxy, every cluster, every supercluster converges toward a single point of unimaginable density. Cosmologists call the moment of maximum compression the Big Bang. Though the name is misleading. It was not an explosion in space. It was an expansion of space itself. Beginning from a state so hot and dense that the physics describing it pushes against the limits of what our current mathematics can handle. In the first fraction of a second, the universe was smaller than an atomic nucleus. In the first 3 minutes, it had expanded enough for the first atomic nuclei to form. In the first 380,000 years, it cooled enough for electrons to combine with nuclei, and allow light to travel freely for the first time. That first light, released when the universe became transparent, is still traveling. We detect it today as the cosmic microwave background. A faint glow of microwave radiation, arriving from every direction in the sky. The oldest light in the universe. Emitted 13.8 billion years ago from a region of space that now sits 46 billion light-years away. The cosmic microwave background is the ultimate demonstration of what the light year does to time. It is not light from a star or a galaxy. It is light from the universe itself. From the moment it first became possible for light to exist as a traveling phenomenon, rather than being instantly reabsorbed by the dense plasma that filled all of space. Looking at the cosmic microwave background is looking at the universe at an age of 380,000 years. A moment so early in cosmic history that no stars had yet formed. No galaxies had yet assembled. No heavy elements existed anywhere. The universe was a nearly uniform sea of hydrogen and helium, with tiny fluctuations in density that would eventually, over hundreds of millions of years, collapse under gravity into the first stars. Those fluctuations are visible in the microwave background as faint variations in temperature, 1 part in 100,000, mapped in extraordinary detail by satellites, including WMAP and Planck. Every structure in the universe today, every galaxy, every cluster, every supercluster, every planet and ocean and living cell, traces its origin to those tiny ripples in the oldest light we can observe. What expansion means for the light year, taken to its fullest conclusion, is that the ruler itself is not fixed against a static background. It measures journeys taken through a medium that was different at the beginning of the journey than at the end. A light year traveled 13 billion years ago covered the same distance in absolute terms as a light year traveled today, 5.88 trillion miles of travel. But the universe those light years were crossing was denser, hotter, and expanding at a different rate. The context changes, even as the unit stays constant. This is why cosmology requires not just the light year, but an entire mathematical framework, general relativity, to describe how light moves through expanding space over billions of years. The light year is the unit. General relativity is the grammar. Together, they allow us to read the universe's history from the light that has been crossing it since the beginning. Edwin Hubble looked through a telescope at faint smudges of light and found that the universe was bigger than anyone had imagined. And that it was growing. Every measurement made since has confirmed and extended that finding. The light year, which already strained human intuition when applied to the distance between stars, becomes something almost purely mathematical when applied to the full scale of an expanding cosmos. It is a unit that connects the familiar to the unimaginable. The 8 minutes of sunlight warming your skin to the 13.8 billion year journey of the oldest light in existence. Both are measured in the same unit. Both obey the same physics. And both point toward the same conclusion, that the universe is not just larger than we imagined, but larger than we are capable of imagining. And that the light year is the closest thing we have to a bridge between those two conditions. Everything discussed so far has treated the light year as a passive unit. A ruler laid against the cosmos to measure what already exists. But the light year has an active consequence that most people never consider. One that reaches directly into the question of whether anything else is out there, and whether, if it exists, we could ever know. The speed of light is not just a measurement tool. It is a speed limit. And that speed limit does not only constrain how fast we can travel. It constrains how fast information of any kind can move. It constrains how fast we can communicate. It constrains, in the most fundamental sense, how connected any 2 points in the universe can ever be. Consider what it would mean to make contact with a civilization orbiting a star 10 light-years away. 10 light-years is an almost trivially small distance by cosmic standards. It is practically next door. The Milky Way is 100,000 light-years across. 10 light-years is 1/10,000th of that. And yet, a message sent at the speed of light to a civilization 10 light-years away would take 10 years to arrive. Their reply, also traveling at light speed, would take another 10 years to return. The minimum possible round trip for a single exchange of information is 20 years. Not because of any limitation in our technology. Not because we haven't built fast enough transmitters or sensitive enough receivers. Because the universe does not permit information to travel faster than light. And 10 light-years of space contains 10 years of unavoidable delay in each direction. Now, extend that to realistic stellar distances. The nearest star cluster to our solar system, the Hyades, sits about 153 light-years away. A conversation with a civilization there would have a minimum round trip of 306 years. No living person who sent the first message would survive to receive the reply. The civilization that answered would be communicating with the grandchildren of the people who asked the question. The galactic center, where the density of stars is highest, and the probability of finding a long-lived civilization might therefore be greatest, sits roughly 26,000 light-years away. A round-trip message exchange with anyone near the galactic center would take 52,000 years. That is longer than all of recorded human history, twice over. The light year does not just make the universe large. It makes it almost perfectly isolated, even at the speed of light. This isolation has a name in physics. It is called the light cone. A concept from Einstein's theory of special relativity that defines precisely which events in the universe can influence which other events, and which cannot. Every point in space and time sits at the apex of a cone that expands outward and forward at the speed of light. Only events within that cone can send information to the apex. Only events within the forward cone can receive information from it. Everything outside those cones is causally disconnected from that point. No force, no signal, no influence of any kind can bridge the gap. The light cone is not a practical limitation waiting to be overcome by sufficiently advanced technology. It is a structural feature of spacetime itself. As fundamental as the dimensions of space and the direction of time. What this means for the search for other civilizations is something that astronomers and physicists have been grappling with since Frank Drake pointed the first radio telescope at a nearby star in 1960. Even if the galaxy is full of technological civilizations, the light year imposes a silence that has nothing to do with whether those civilizations are broadcasting. It has to do with timing. A civilization that existed 1 million years ago and broadcast radio signals for 10,000 years before going quiet would have left an expanding shell of electromagnetic radiation crossing the galaxy right now. That shell is real. It is out there. But it is thin. Only 10,000 light-years thick against a galaxy 100,000 light-years across. And it is expanding. The probability that Earth sits within that shell at this specific moment in cosmic history is small. The civilization is gone. Its signals are passing through, or have already passed, or have not yet arrived. This is one of the most underappreciated aspects of the Fermi paradox. The question of why, given the age and size of the galaxy, we've detected no sign of other civilizations. The silence does not require that civilizations are rare, or that they destroy themselves. It is consistent with a galaxy full of civilizations that simply do not overlap in time and space at the resolution the light year imposes. Two civilizations separated by 50,000 light-years, who each exist for 10,000 years, have an extraordinarily small probability of their signals coinciding at the same point in space during the narrow window when both are broadcasting. The universe is not just spatially vast. It is temporally vast. And the light year connects both dimensions simultaneously. Measuring distance in units that are also units of time. The practical consequences of this for any attempt at interstellar communication are severe. Every strategy ever proposed for making contact with another civilization runs directly into the light year as an obstacle. Radio signals travel at the speed of light, so they face the full delay. Laser pulses travel at the speed of light. Neutrino beams, if we could ever produce them in the quantities needed for communication, travel at effectively the speed of light. There is no known physical mechanism that allows information to travel faster. Quantum entanglement, which produces correlations between distant particles that appear instantaneous, cannot be used to transmit information. The correlations are real, but the information content cannot be controlled in a way that would allow a message to be encoded and decoded faster than light. Every loophole that physics has been asked about has been closed. The speed of light is the wall. And the light year is the measure of how thick that wall is between any 2 points in the cosmos. Some physicists have proposed theoretical frameworks that might allow something like faster-than-light travel or communication. The Alcubierre drive being the most mathematically developed of these proposals. The idea involves contracting space in front of a vessel and expanding it behind, creating a bubble of flat spacetime that moves through the surrounding space faster than light without anything inside the bubble moving faster than light locally. It is consistent with the mathematics of general relativity in a narrow technical sense. It also requires exotic matter with negative energy density. A substance that has never been observed, and whose existence is theoretically uncertain in quantities that some calculations suggest would need to exceed the mass energy of the observable universe. It is a solution that exists on paper, in a very specific sense of the word exists. No physicist working seriously on propulsion regards it as a near-term or even medium-term possibility. The light year remains the wall. What remains, then, is a universe in which the speed of light is absolute. Distances are measured in the time it takes light to cross them. And any two civilizations separated by those distances are separated not just in space, but in time, by exactly the same amount. A civilization 1,000 light-years away that we detect today is showing us what it looked like 1,000 years ago. If we reply, our reply will arrive 1,000 years from now. The civilization we are replying to will be 2,000 years older than the one we detected. It may be unrecognizable. It may be gone. The light year does not just measure the distance. It measures the unbridgeable gap between any two moments in the history of two civilizations trying to find each other across the dark. And yet the search continues. Not because the obstacles are small, but because the question is large enough to justify the attempt anyway. Every radio telescope pointed at a nearby star is an acknowledgement that the light year is real. That the delay is real. That the isolation is real. And that none of it is reason enough to stop listening. The signal, if it ever comes, will be old by the time it arrives. The civilization that sent it may no longer exist in any form we would recognize. But the fact of its existence, encoded in light traveling across years, or decades, or centuries of empty space, would be the most important measurement in the history of science. The light year is what makes that signal possible. It is also what makes it so achingly, structurally, physically difficult to find. There is a final consequence of the light year that brings everything back to the planet you're standing on right now. Not the distant galaxies, not the expanding universe, not the theoretical civilizations separated by thousands of light years of silence. The light year has something to say about Earth itself. About the signal this planet has been sending into the cosmos. About how visible we are. About how long that visibility lasts. And about what the geometry of light speed means for the odds that anyone has ever noticed us at all. Humanity became electromagnetically detectable from interstellar distances at a specific moment in history. The first radio signals powerful enough to escape the atmosphere and travel outward into space date to the early 20th century. The first television broadcasts followed in the 1930s and 40s. Military radar systems, the most powerful signals Earth has ever produced in terms of raw electromagnetic output, came online during and after the Second World War. Those signals did not stop at the atmosphere. They kept going. Expanding outward in every direction at the speed of light. A growing sphere of electromagnetic noise. Announcing that something on this planet had learned to manipulate radio waves. That sphere is now roughly 100 light-years across. It contains approximately 15,000 stars. 100 light-years sounds like a large bubble. Against the scale of the Milky Way, it is not. The galaxy is 100,000 light-years across. Our electromagnetic bubble covers 0.1% of that diameter. If you shrank the Milky Way to the size of a continent, our radio bubble would be roughly the size of a small building sitting somewhere in the middle of it. The 400 billion stars in the galaxy, the vast majority of them, have never received a single photon produced by human technology. We have been broadcasting for a century, and we remain essentially invisible to almost the entire galaxy. The light year is what turns 100 years of radio transmission into a bubble so small it barely registers against the full scale of the cosmos we're trying to reach. But the bubble is not just small. It is also uneven in time. The outermost edge of that 100 light-year sphere is currently receiving the very first radio signals humanity ever produced. The faint and primitive transmissions of the early 20th century. A civilization sitting precisely at the edge of our bubble, with instruments pointed at our star at this exact moment, would be detecting signals from 100 years ago. Before television. Before radar. Before the atomic age. They would have no way of knowing what came after. The middle layers of the bubble contain decades of television broadcasts, radar pulses, and early satellite communications. Only the innermost layers, the most recently transmitted signals, reflect anything like the civilization Earth is today. The light year means that our signal is not a single coherent broadcast. It is an onion. Each layer showing a different era of human technological development. Each layer currently washing over a different set of stars at a different distance. There is something deeply strange about this when you follow it fully. Right now, at this moment, the television broadcasts of the 1960s are washing over stars roughly 60 to 70 light-years away. The moon landing, broadcast globally in 1969, is currently arriving at stars approximately 56 light-years from Earth. The first radio signals strong enough to have any realistic chance of detection by a civilization with technology comparable to our own are somewhere around 80 to 100 light-years out. Currently reaching the stars at the outer edge of our bubble. Every star within that bubble is receiving a snapshot of a different moment in human history. The snapshots arranged in reverse chronological order. The oldest signals furthest away. The newest signals closest in. The light year has turned our history into a physical structure, expanding through space. Meanwhile, Earth is changing its signal. The transition from analog to digital broadcasting. From omnidirectional transmission to targeted delivery. From open radio signals to encrypted, compressed data that looks indistinguishable from noise. It is already underway and has been for decades. The signals leaking from Earth into space are not getting stronger. They're getting weaker. Broadcast television, which once pumped powerful omnidirectional signals into the sky, has been largely replaced by cable, fiber optic, and streaming delivery systems that keep their signals on the ground. Military radar is shifting from systems that spray energy in all directions to phased arrays that concentrate it in tight, controlled beams. Cellular networks use low-power transmitters aimed at the surface, not the sky. Earth in 1970 was electromagnetically loud in a way that Earth in 2026 is not. The window during which this planet produced its strongest detectable signal may already be closing. This has an implication that cuts both ways. If Earth's detectable window is narrowing, then the windows of other civilizations are likely narrowing, too. And for the same reasons, efficiency selects against broadcast. Any civilization advanced enough to develop radio communication is also advanced enough to eventually replace it with more efficient, directed systems that do not leak into space. The window between first radio transmission and electromagnetic silence, the period during which a civilization is both technologically capable of producing a detectable signal and not yet advanced enough to have switched to systems that do not produce one, may be surprisingly short. A few centuries at most. Possibly less. Against the 13.8 billion-year age of the universe, a window of a few centuries is not a window. It is a camera shutter click. Two civilizations would both need to be in their leaky phase at the same time. Within detection range of each other. With instruments pointed in the right direction. At the right frequency. During that narrow overlapping window. The light year enforces the delay. The expansion of the universe enforces the isolation. The brevity of the detectable window enforces the timing problem. All three work together to make contact not just difficult, but statistically improbable in a way that does not require any civilization to be hostile, or silent by choice, or filtered out by catastrophe. This silence may simply be a consequence of geometry, time, and the speed of light. Operating simultaneously across a galaxy 100,000 light-years wide. There is a thought experiment that makes this concrete. Imagine two fireflies in a forest the size of a continent. Each firefly flashes once for a fraction of a second at a random moment during a single night. What is the probability that either firefly sees the other's flash? The forest is too large. The flash is too brief. The timing too random. Both fireflies are real. Both flashes occur. Neither is ever witnessed by the other. The continent-sized forest is the galaxy. The fraction of a second flash is a civilization's electromagnetic window. The light year is the darkness between them. The medium through which the flash must travel, imposing a delay that may be longer than the flash itself lasts. Two civilizations could exist in the same galaxy, both broadcasting, both listening, and miss each other by 10,000 years and never know the other existed. This is not a pessimistic conclusion. It is a precise one. The universe is not empty because life is impossible, or because civilizations inevitably destroy themselves. Though those possibilities remain open. It may appear empty because the light year, applied to the full scale of the cosmos and the full brevity of a technological civilization's detectable phase, produces silence as its natural output. The mathematics of overlap, of two narrow windows coinciding across vast distances and vast time scales, generates a number close to zero, even in a galaxy teeming with life. The silence we observe is consistent with abundance. It is consistent with a cosmos full of civilizations that have risen and fallen, and risen again, across billions of years. Each one separated from the others by the one thing that cannot be negotiated with, cannot be engineered around, and cannot be made to move faster than it moves. Light. Step outside on a clear night and look up one more time. Every point of light you see is a message from the past. Traveling across light years of empty space to reach your eye at this specific moment. The nearest stars are showing you years ago. The furthest visible to the naked eye are showing you centuries ago. The faint smear of the Milky Way stretching across the sky contains light that has been traveling for thousands of years to arrive tonight. None of it is showing you the present. All of it is showing you history, layered and compressed into a single moment of observation. The universe is not a place you can see. It is a place you can only remember. One light year at a time. Reaching backward through time with every glance upward. Surrounded by messages that left their sources long before you existed. Crossing the dark at the only speed the cosmos permits. Arriving now, and carrying in every photon the distance they have traveled, and the time that travel required. That is what a light year is. Not just a number. A unit of separation, of history, of silence. And of the unbridgeable, beautiful gap between everything that exists and everything that can ever know it exists. The terrifying truth. Even in a universe bursting with possible life, the odds of us ever hearing a single, faint whisper back are less than 1 in 65 billion.